All right, let's break down one of the most common molecular shapes out there, the AB3E shape. So, ever wonder why molecules aren't just flat? It's a great question. It all comes down to Vsepr theory. Basically, electrons need their personal space. To get it, we gotta start with the ideal situation. Picture 4 electron pairs, all of them bonds. This gives you something like methane. It forms a perfect symmetrical tetrahedron. And the magic number here, 109.5 degrees. Lock that in your brain, it's important. Okay, now for the twist. What if one of those pairs is actually a lone pair? So we're going from a perfect AB4 molecule to an AB3E. See that key difference? Here's the deal. That lone pair is way bigger and much pushier than a bonding pair. Yeah, there's a definite pecking order for Apollyon, and lone pairs are at the very top. Let's look at a real-world example, ammonia. It's your textbook AB3E molecule. Think of that lone pair as an invisible bully shoving all the other bonds around. It's a simple cause and effect. The lone pair hogs space and squeezes the other bonds together. Okay, this is a crucial point. We talk about geometry and shape in 2 different ways. If you include the lone pair, the electron geometry is still tetrahedral. But if you only look at the atoms themselves, the molecular shape is trigonal pyramidal. And you can see the proof right there in the numbers. Let's check out the angles. Remember our perfect methane molecule? Its angle was exactly 109.5 degrees. Now look at ammonia. That angle gets squished down to about 107 degrees. That tiny difference is the smoking gun. It's proof of the lone pair's power. So the takeaway is this. Atoms define the shape, but those invisible lone pairs are really in charge. Which leaves us with a fun question. If one lone pair does this, what happens with 2?